Okay, welcome and thanks for attending. This talk is called Diving Headfirst into Rustland, and I designed it as a talk to help C++ developers that maybe want to try Rust not get lost while trying to start learning Rust. So about me, I'm currently employed at the Avalanche GmbH in Bochum. I've been using C++ for a very long time, basically since I can remember. I have a background in reverse engineering and game hacking, so usually low-level stuff. And upon a friend's recommendation, I tried Rust around 2 years ago, and I've been completely loving it. So I'd like to give back with this talk what I would have loved to have watched myself back then. Yeah, that just says that. Okay, we will quickly, but not too in-depth, go over the style of Rust code, expressions, and parts of functional programming. We'll be going over the memory management, the package management, pattern matching, enums, or tagged unions, error handling, composition as the model of OOP, as an alternative to the OOP, for example, in C++. And we'll also take a quick look at generics. First, though, I want to quickly remind everyone that the documentation for Rust is absolutely amazing, and that this is not a replacement for any of these by far. And if you've read docs before and don't like that and haven't read these before, I recommend trying them because they are really, really good. So about Rust style, compared to a lot of other languages, Rust enforces a pretty strict code style guideline, as opposed to other languages where it's more laissez-faire. Everybody can have their own style. So reading Rust code bases almost always feels roughly the same, which is good if you like the style. If you don't, maybe not. Oh. Then expressions. So Rust makes heavy use of expressions. A lot of constructs like blocks, if expressions, and match expressions. Sorry. Okay, I'm just going to read that one. I'm blocking. A lot of constructs that are statements in other languages are expressions in Rust. For example, blocks, if expressions, and match expressions. This means, for example, if you want to quickly compute a value and just place it as an argument somewhere, you don't have to pre-compute it, put it in a variable, and then assign it. You can then pass it. You can just put that block right there and let it evaluate. C often uses, or basically only uses, switch cases for jump tables and having a conditional branch with a huge amount of potential branches. And Rust, with its matching match expression, allows a much cleaner syntax than what C users might be used to. As I said before, a block of code is also an expression, which surprised me at first. I was under the impression, code is procedural. It's a procedure, not an expression, but it really does make code a lot cleaner and more beautiful if one knows how to use it. Here's an example of a block of code as an expression. Just very useful in general. Then functional programming. So Rust borrows a lot of concepts from languages like OCaml. It makes heavy use of iterators, making it easy and efficient when operating on collections of data. Usually it's functions that call a closure for every element in a collection and do a certain thing, which you might be familiar with from other languages. I'm sure this is not unique to OCaml or Rust. Then the memory management. One of the biggest talking points when I heard about Rust at first was that memory bugs were harder to make, I guess. And at the time I thought, C++, you can make those errors, but just don't make those errors. It's not worth it to have the compiler hold your hand and, like stop you from doing stuff you want to do. But then when I actually did learn Rust, at first it did feel like somebody was holding me back. But after a while, your code just adjusts and you don't feel the borrow checker at all, and your code is safe. So I believe if this is like an argument for you to not try Rust, to reconsider. The Rust compiler enforces memory safety at compile time this way, using a few rules. Every variable has an owner, and that owner has a scope. When the variable goes out of scope, the variable is dropped, and a certain trait allows the variable to clean up after itself if necessary. The default implementation simply moves the value into a scope and then leaves the scope. Variables are also moved by default, and references to a variable can only be given out in line with Rust's borrowing rules. Oops. That is way farther back. As I'm pretty sure a lot of you know, there can be only one mutable reference to a variable at a time, and no immutable references while the mutable reference is active. This prevents data races and use after exactly. And no immutable references while the mutable reference is active. If the variable is not mutably borrowed, it can be immutably borrowed as often as desired, since when nothing's modifying it, you can't have a data race. This is achieved using lifetimes, which I actually like. My friends don't really like lifetimes. Every variable has a lifetime determined at compile time, and for example, a struct can hold a reference to a variable only if the compiler can ensure that the variable will live longer than the struct will. And we skip right over to package management, which I think is one of the nicest things about Rust. After years of shoving shared objects around and linking, just typing in the package name and a version makes it very, very nice to use. It downloads, compiles, and links dependencies automatically, and Rust has a pretty unified package repository called crates.io that everybody can publish packages to and immediately pull down and compile if they want to. Also, adding a dependency from a Git repository or a path is very easy. So you can have multiple projects in a Git repository and simply have them as dependencies on each other. It is also consistently used on almost every single Rust project. So you can have a cargo project, and every other project basically that you will ever encounter will also have cargo. A Rust project is called a crate. It can be either a library or a binary crate. They can expose feature flags that the end user can select and basically shape the library's behavior to their requirements. Crates are versioned using Semver, and when adding a crate as a dependency, you specify a constraint to tell cargo which versions are fine to use. It will pull the newest that matches the criteria and then put it in a log file. And unless you manually tell it to update or delete the log file, it will keep using that version since it's valid near constraint. Now, pattern matching, which I didn't really think was a thing before I even touched Rust. So it's such an amazing concept, honestly. Makes code so much better. It allows you to match patterns on values. For example, matching a literal, an enum variant, a struct variant, more. In C, for example, you would use, did I not say that before? I did. In Rust, the switch syntax is improved upon with a match expression that allows writing more readable code. And it looks something like this, which I think is better than case 0, print line, and then a break. Enums, my favorite topic here. Rust enum variants can not only be numeric, as in some other languages, but contain any arbitrary type the user wants. For example, Rust has two very common enums that are basically used everywhere in Rust code: option T and results T error. Option can be one of two variants, none and some. So there's no need for null sentinels. If a function can conditionally return a value, for example, option is used to let the user easily match on it and decide what to do. Result can be one of two variants as well, OK and This time, though, the OK variant, which would be an equivalent to none before. No, never mind. It does contain a value T, and contains a value E. It is the enum used for error handling, And if a function can fail, it will simply return a result. And this result, T will be the type you want to return, and E the type containing the error information you want to pass. This makes it easy for the users to match on it and maybe panic if the error is severe or ignore it. It's a user's choice, but I think it's a very good solution. This is an example of how option works. You can match on an option and have it, matched. There's also more complex stuff you can put in an enum, which is actually really nice. You can match on the structs, or quote-unquote structs, members as well. Here we come to error handling. Other languages usually use exceptions, and Rust uses result for error handling, where E is an enum or struct containing error information. The end user can match and decide what to do. And there's also crates that try to make this easier, most notably anyhow on this error, which I really like. I would recommend taking a look at them if you are serious about trying Rust. Here's a code, an example code of using result. So we have an error enum. We have a function that may or may not return an error. And at the very bottom, we have a match statement where we call the error propagation function, which, it calls may error. And instead of directly matching on it, it uses this question mark operator. And that question mark operator basically means if it's okay, then we evaluate this expression to the value contained in okay. And if not, we return back the error, which is really nice instead of having to not throw up, but return the results back up. And then there's an example on using unwrap, which is a very quick and hacky way to develop code when you don't really care about the error state. The error state may be not handleable, so unwrap will crash the program if the error variant is matched. Otherwise, it will return okay. So languages like C++ use inheritance, and Rust uses an approach called composition. The main concept in composition in Rust is a trait. A trait is basically a definition of behavior for a certain object, and many types can have many traits associated with them or implemented. If you want to, for example, have dynamic code in, say you want, again, C++, you want an animal, but there may be dogs and cats. Well, maybe you just want an animal that can walk. So you take a box with a dynamic animal trait. This is a fat pointer with vtable information and can be used to, well, dynamically work with objects matching this trait bound. Generics are a way to have functions, structs, and more take any type matching certain bounds. So this is also similar to templates in a way in C++. And code is generated at compile time accordingly, generating multiple versions of the construct for each real type used. So if you, for example, give the example function an unsigned 32-bit integer and a signed one in two different places, this function will exist twice for the different types in the resulting binary. And miscellaneous things that I would have loved to hear about, because I was confused at it at first. As any body of code is an expression, the Taylor expression of the block is what it basically evaluates to. By extension, functions do not need a return statement, but can simply place their return value as a Taylor expression, which is actually really cool and looks good. Then I quickly wanted to touch on debug derives, because I did not know these existed until like a month after I started. And they're just really useful for quickly seeing the workings of your binary without having to attach a debugger. And with that, thank you for attending. And if you have any questions, feel free to ask them.